Okay, in this lesson we're going to talk about series in general and an arithmetic series. So to start off, what is a series? A series is an expression formed by adding the first n terms of a sequence. And so really a series is just a sum of a sequence. Okay, it can be a part of a sequence, or it can be a whole sequence, but a series, think about it just as a sum of a list or sum of a sequence. So, one notation that we use when we are calculating series is called summation notation. Okay, in summation notation, the sum of a finite sequence is denoted using these characters. So the first thing you'll notice is this big E looking character. This is actually the Greek letter sigma. Okay, it's a capital Greek letter. Sometimes we'll even call this sigma notation. Okay, and we've also got these numbers underneath and on top of it. And then to the right of it, we've got this A sub k. So let's break it down and we'll read what it says, and then we'll break down each of those variables. So if we want to read this, we read the sum of our sequence A sub k from k equals 1 to n. All right, where A sub k is our sequence in explicit form. Okay, so we can't plug a recursive formula into sigma notation. And we've got this k equals 1. K is the index, and this 1 is kind of our starting term number, and the n is our last term number, or the end of our sequence. Okay, it's the upper limit. So let's look at an example. Okay, example number 1. We've got the sum of 3i from I equals 1 to I equals 5. Okay, so we're going to sum up the terms 1, 2, 3, 4, and 5 by plugging those values into this sequence function here. All right, so the first thing I want to do is I want to list out this sequence. So my first term, I'm going to plug in a 1. 3 times 1 is 3. I want to add that to the second term in the sequence, so I'll plug in a 2. 3 times 2 is 6. Add that to the third term, to the fourth term, and to the fifth term. We're going to stop at 5 because that's our upper limit on the top. So 3 times 5 is 15. Okay, so this is the our series. So we want to add these up. Okay, we can do some math in our head. We've got a 15 here. We have a 15 between these two and a 15 here. So that makes 45. All right, so the sum of that sequence, first 5 terms, is 45. All right, let's look at another example. We've got the sum of 1 plus k squared from k equals 3 to k equals 6. So now 3, 4, 5, 6, that's going to be 4 terms. So we've got, let's find our terms first, and then we'll add them up. So plug in 3. 1 plus 3 squared. 3 squared is 9, plus 1 is 10. 4 squared is 16, plus 1 is 17. 5 squared is 25, plus 1 is 26. 6 squared is 36, plus 1 is 37. All right. Not doing that one in my head. I'm going to pull out my calculator. 10 plus 17 plus 26 plus 37, and we get 90. Okay, one more example, number 3. The sum of 1 over j factorial from j equals 0 to 4. Okay, so we're starting by plugging in 0 first, and then 1, then 2, then 3, and then we're ending by plugging in 4. So let's find our sequence, and let's add it up. Okay, so if we plug in 0, 1 over 0 factorial, I may just write them like this, and then we'll simplify in our next step. 1 plus 1 factorial, 1 plus 2 factorial, plug in a 3, and plug in a 4. Okay, so now let's simplify. We're going to add up these 1, 2, 3, 4, 5 terms. All right, 0 factorial is the same thing as 1. 1 over 1 is 1. 1 factorial is 1. 1 over 1 is 1 again. 2 factorial is 2 times 1, which is 2, so that's 1 over 2. 3 factorial is 3 times 2 times 1, so that's 6, so 1 over 6. 4 factorial is 4 times 3 times 2 times 1, so that's 12 times 2 is 24, so 1 over 24. Okay, so now we would just add these together. If we find our common denominator and add these up, then we're going to get 2 and 17/24. Or if you plug it in your calculator and round, you're going to get 2.708, and the 3 is repeating. Okay. Okay, so those were just sequences in general. What if we now look specifically at arithmetic series? Okay, or sums of arithmetic sequences. Okay, so let's let a sequence be a finite arithmetic sequence with common difference d. And the sum of the sequence, again, using our sigma notation. But now we've got a shortcut. Now instead of having to calculate each term, we have a formula. So let's look at this formula. Capital S sub n, that just stands for sum. Okay, and again, this just works for our arithmetic finite sequences. Finite just means that there's a countable number. Doesn't go on forever. So we've got n over 2, where n's the number of terms, times a sub 1, which is the initial term. Maybe let's define these. Initial term. This is our number of terms. Okay, and a sub n would be our final term. Okay, so this is kind of neat. So number of terms over 2 times the sum of the first and the last term. Okay, or if we don't know the last term, then we can use this formula here. So let's look at an example. Okay, a corner section of a stadium has 8 seats along the front row. Each successive row has 2 more seats than the row preceding it. If the top row has 24 seats, how many seats are in the entire section? Okay, so they give us an initial value. This is our a sub 1. They give us our final value. This is our a sub n. If we're adding to each row, and this is an arithmetic sequence, it's important to identify that first before you want to go using this formula. Okay, so I'm going to start at 8, and I'm actually just going to start by listing them. If there's 2 more each time, then I'm just going to add 2 until I get to my final term, 24. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 terms. So this is our a sub 9. This is our initial. Okay, so we could just add these up. We could put this in our calculator, add these up, and we're going to find that we get 144. And that's our answer. If we want to test this using our new formula, well, our initial value is 8. Our final value, this is our a sub n, is 24. And our n value is 9, because we've got 9 terms, starting with number 1. So let's plug them into our formula. So S sub n is 9 over 2 times our initial 8 plus our final 24. Okay, 8 and 24 is 32. So we've got 9 over 2 times 32. Let's see, if we try to do some of this in our head, 32 is 32 over 1. 2 goes into 2 once, goes into 32 16 times, and 9 times 16 is 144. All right, so plugging it back into the context of our problem, we're talking about how many seats are in the entire section. So I would say 144 seats in the entire section. All right, next example. Now we've got some sigma notation. We've got the sum of 3k plus 2 from k equals 1 to 20. Now, I certainly don't want to list all of these out, so let's try using our calculator. All right, so our calculator can do sums. If you've got the 84 with the updated operating system, if you press alpha F2, then you'll notice that option 2 is our sigma notation. So if we press enter, then we can say, what did I just push? I pushed our variable button, and I'm already in sequence mode, so it gives me a little n. If you're not in sequence mode, it gives you an x. That's okay. Either one will work just the same. Okay, so n equals 1. We cursor up to our upper limit, plug in a 20, and then we plug in our explicit rule, 3n, so n in place of the k, plus 2. Press enter, and it gives us our sum. Pretty handy. Okay, if you're on an 83, then we've got to work around a little bit. We're going to use our sum combined with the sequence function that we talked about in our last lesson. Okay, so again, we're going to go to second stat. We're going to go over to ops, and we're going to go over to math menu and cursor down to our sum option. And then we're going to go back to second stat, go over to ops, and select sequence. Okay, so again, we're going to sum a sequence. It kind of makes sense when we think about what we're telling our calculator to do. Okay, so we're going to sum a sequence, and we're going to put in our function rule first. Again, explicit rule, 3n plus 2. We're going to put in what our variable is. That's n. Each of these separated by commas. Our first term number, our last term number, and we can tell it to step by ones, although it understands if we don't put a number in there. Okay, and we get the same thing, 670. All right, so now let's look at something that's not a finite series, an infinite series. So sum always applies to a finite series, summing up an actual countable number of terms. Okay, but using limits, we can add an infinite number of terms. We call that an infinite series. Series has an E in it. All right, so infinite series. We've got our sigma notation again on top. Instead of having a number on top, we have our infinity symbol. Okay, so the sum of some sequence, a sub n, from 1 to infinity, and we use our ellipsis dots to note that it just keeps on going. Okay, this is not technically a true sum because it is getting bigger for each bigger term that we plug in. But we can approximate it by finding partial sums that approach certain limits. Okay, and if we have an infinite series, it can either converge to a certain sum or a certain limit, or it can diverge, which just means it does not have a sum. It doesn't actually approach a single value. So let's look at a couple of examples. Okay, find the first 5 terms in the sequence of partial sums. And does it converge or does it diverge? So what this term partial sums means is just as we are summing terms, we're going to kind of keep a tally. So the sum of the first term is just itself. Okay, we're not adding it to anything. But now when we add it to the second term, if we give a sequence of partial sums, then the first term plus the second term is going to be 11 hundredths. And then if we add in 1 thousandths, then our next term is going to be 111 thousandths. If we add in this 1 10,000ths, then the next partial sum is going to be 1,111 10,000ths. And as these partial sums increase, as we keep adding on more and more terms in this sequence, then it's going to approach, it's going to get closer to the sum of this series. Okay, and as we can tell, if we do our little ellipsis dots, it keeps on going, and it's going to approach just 0.1 repeating. The ones are just going to keep on repeating if we continue this sequence. And that is the fraction 1 over 9. So it converges on 1 over 9. Sometimes you'll hear it say it's a convergent series. All right, let's look at number 2. We've got 10 plus 20 plus 30 plus 40 and so on and so forth. Again, these dots are the key to tell us this is an infinite series, that it goes on without limit. So if we do our partial sums again, first one is 10, 10 plus 20 is 30, plus 30 is 60, plus 40 is 100, and we're never going to stop increasing. We're actually going to continue to increase by a bigger number each time. Okay, so it's never going to actually converge on a particular number. So this is an example of a divergent series. Okay, it has no sum. All right, one more example. We've got 1 minus 1 plus 1 minus 1 plus 1 and so on and so forth. Again, looking at our partial sums kind of clues us into whether or not we have a convergent or a divergent series. First partial sum is 1. 1 minus 1 is 0. Add 1 to that sum. We get 1. Take 1 away, 0. And we can see where this loop is going to go forever and ever. So this is a different example of a divergent series. Okay, so basic series using summation or sigma notation. Make sure you're comfortable with putting those in your calculator using either the sigma notation or the sum sequence command. Make sure that you can list partial sums and you can tell whether a series converges or diverges.